Hey, Jacob.
I don't have my.
I usually give those at the end.
Oh, okay.
All right, it's 4 o'clock, so let's go ahead and get started. Good afternoon, everyone. How's everyone doing today? Good. So yesterday morning, I finished grading your midterms, and so your scores for that are on Canvas right now. Okay, and so I brought them here with me today. And so if you're here in person, you can pick it up after the class. Okay. In terms of the score, you guys are pretty good. So the average, so the maximum amount of points was 40, and so the average was about a 32, a little bit over 32 out of 40. Okay, so that's sitting right about at an 80%. So that's actually perfect in terms of where I want the class average to be. Yeah. I don't know if anyone got a perfect score, but the maximum amount of points was 40. Yeah, I'd have to look at the grade book again just to make sure. But I don't think anyone got a perfect score on the exam, but the maximum possible was 40, and the average was 32. Yeah. Okay. Right, and so the feedback that I have on your exams is on there, and I know a couple of people have emailed me the last couple of days about feedback too, and I think I've responded to everyone. But if you want to talk about your exam, I'm definitely open to doing that. And so after I give back your exam, or if you want to talk about your score, I'm always free to do that. Okay. I posted the solutions on Canvas, and so you can check the posted solutions to see what I was looking for each question. Because for each question, I was looking for some fairly specific things. And so what I saw a lot, quite often, was I saw some answers that were written, and it had a little bit. It was a little bit relevant to what the problem was asking for, but a lot of times I was looking for certain specific things. And so if you didn't have those specific things, I mark you down for. Although in a lot of cases, I did give you some points for talking about something, somewhat relevant. Okay. Okay. And so that's the exam. Are there any questions on that or any questions on anything before we get started for today? Okay. All right. And so I'll pass those out at the end of class today. Okay. And so for the topic for today, we're going to be going over calculations in terms of upper extremity biomechanics. Okay. And in particular, we're going to be learning a new technique today. Or it's not really a new technique. It's basically just free body diagrams. But we're going to be applying those free body diagrams to your limbs. And we're going to be using that to compute muscle forces and joint reaction forces in the body. Okay. And so this is kind of the first point in the class where we're really going to start to actually do some calculations that can be actually useful for engineering. Okay. And the and the type of analysis that that this is called static biomechanical analysis. Okay. It's just normal statics. It's just that it's because it's applied to biological systems, they call it static biomechanical analysis, but in reality, it's just statics. Okay. Okay, so let's go ahead and get going. Okay. And so the idea with static biomechanical analysis is that we want to do, we're going to form free body diagrams. Of body segments. Oftentimes, we're going to be looking at situations where the human body is supporting some kind of external load. Okay. Right. And so basically, you're going to have the external loads applied on the body. And oftentimes, the bones and the muscles and the body segments themselves have weight that need to be supported. Okay. Okay. And so what we're going to do is we're going to basically use these free body diagrams to perform static analysis. Okay. Right. And so remember, all that means is basically we're going to sum up all the forces. Okay. We're going to be looking strictly at 2D situations just because that's the best that I can draw. Okay. And so we're going to sum up all the forces in the x direction, set it equal to 0. Sum up all the forces in the y direction and set them equal to 0. Okay. And we're also going to sum up the moments in the problem and set them equal to 0 as well. Okay. And so we're going to be considering rigid body rotation, or at least lack thereof. Okay. And in particular, oftentimes when we sum up the moments, we're going to be summing them up around a joint in the body. Okay. And so you're going to see me use this terminology, sum of the moments around J. Okay. And then what we're looking for in this analysis, and so by forming these 3 sets of equations here, we're going to be able to solve for the muscle forces. Okay. Muscle forces and also joint reaction forces. Okay, so those are going to be our two main outputs. Okay. And these are the forces that are basically, that basically the body needs to exert, or these are the forces that get placed on the body in order to keep these situations in static equilibrium. Okay. Right. And so I think, and so in principle, it's not that difficult. I think if, you've probably all have done this a bajillion times up to this point in your educational career, but now we're going to be doing this kind of applied to biological systems. And we'll talk about, after we solve for things like, how much muscle force is being applied and how much forces are being, applied or loaded at the joints, what kinds of biological implications this is going to have for people. Okay. All right, any questions on this before we jump right into an example? Okay. All right, so let's go ahead and do, let's start with the pretty simple example. Okay. And so let's consider a situation where we have an elbow held at 90-degree flexion. Okay. And in this configuration, we'll say that this person is supporting a weight that they're holding in their hand. Okay. Okay. And so schematically, it might look something like this. Okay. And so let's say that we have an external weight right here, okay, represented by a box W, okay. And then on the interior of this of the forearm here, let's just consider one of the forearm bones. And so we have two of them in there. And so normally we have both the radius and the ulna, but just for simplicity's sake, let's just consider just the bigger one. So let's say that we're just considering the ulna, okay. Okay. And then acting on this limb right here is going to be the biceps brachii muscle, okay. And so let's say that we have a muscle that attaches kind of like this. I drew this poorly, and so the muscle is bursting out of the person's arm, and so that normally doesn't happen, but I didn't really have that much room over there. Okay. And for this simple example, we're going to assume that this is the only muscle that's active. Okay. And so in reality, we learned last time that we have several bicep flexors, right? Or elbow flexors, I'm sorry. And so there's several muscles that can aid in this. But just for this simple example, we're just going to consider just this one, okay? Right. And also for simplicity, let's assume that this muscle acts vertically upwards. And so let's say that we have a muscle force that goes vertically upwards like that. Okay? And we'll say that's an unknown muscle force, Fm, that we're going to solve for in the problem. Let me go ahead and draw in the weight of the object. We'll call that W. Okay. And then in addition, one more force that we're going to consider is the weight of the forearm itself. So we're going to assume that the forearm weighs a certain amount. Okay. And so we'll call that WA. And so right now we have three forces in our system. We have the bicep muscle force, we have the weight of the lower arm, and we also have the weight of the object that we're carrying. Okay. Last thing that I'm going to draw into this figure is an approximation of the joint. Okay. And so this dot right here, this is the elbow joint. Okay. And then at the elbow joint, we're going to have reaction forces. Okay. And so mechanically, you can think of the elbow joint as basically like a pin joint, right? And so we're going to assume that this joint kind of, for this static analysis remains fixed in space, but you can rotate around it. Okay. And so just like a normal pin joint, we're going to have reaction forces at this joint as well. Okay. And so the reaction forces, we can break it down into two components. Okay. And so let's say that we have a reaction force Jx acting in the x direction and a reaction force Jy that's acting in the y direction. Okay. And so the goal for this problem is that we're going to solve for all of the unknowns in the system. Okay. And the unknowns are going to be Jx, Jy, and Fm. And so this is pretty typical of these static problems that we're gonna see for the next few weeks. Okay? And so I'm going to be giving you a static situation, and then usually the things that you're going to solve for in these situations are the reaction forces at the joints, and also some kind of unknown muscle force. Okay. And so to do this, all we're going to do basically is we're going to sum up all the forces in the x direction, set it equal to 0. Right? We're going to sum up all the forces in the y direction, set it equal to 0. Okay? And we're going to sum up all the moments and set them equal to 0 as well. Okay? And so what this will give us is 3 equations, right? 3 algebraic equations. And we can use those to solve for our 3 unknowns. Right? And so we have a perfectly, kind of a perfect system for us to solve for what we need to. All right, any questions on the example setup here? Okay. All right, so let's go ahead and do that. And so, I have the figure for what we're examining here, but it's a little bit messy. And so first thing I'm going to do is I'm going to clean this up and then put it in terms of, as simple of a free body diagram as possible. And so the simplest one that we can come up with is just a straight line, okay? And so on this side, we have the joint on this side, okay? And so we have Jx acting in the x direction. We have Jy acting in the vertical direction, okay? All right, so next let's go just from left to right and then put in all the forces that we have, okay? But first we have the muscle force, okay? That's Fm. Then we have the weight of the arm, and so that's Wa. Okay. And then we also have the weight of the object, which we just call W. Right, I'm leaving everything in terms of symbols for now, just because I want to solve for the result, and then I want to kind of analyze, how the result depends on each of these different parameters. But I think that's always kind of a useful thing to do, especially when you're first kind of starting out to do this kind of analysis. Right. And then let's assume that we also know all of these moment arms right here. Okay. And so we're going to assume that we know how far away the forces are acting from the joint. Okay? And so for this distance right here, we'll call this Lm, okay? Because it's the moment arm for the muscle force. Okay? The next distance, we'll call this LA because that's the moment arm for the weight of the arm. And then the longest distance, we'll call it LW because that's the moment arm for the external weight. Okay. All right. And so let's just go ahead and start forming our static equations, right? And so first, let's sum up all the forces in the x direction. Okay. And we're going to assume that we have a standard xy, xy directions here. So the x direction is horizontally left and right, and the y direction is vertically up and down. Okay. And so the sum of all the forces in the x direction, here we only have just one force. Okay. So the only horizontal force that we have here is Jx. Okay. And this is going to be set equal to 0. Okay. In order to maintain static equilibrium. And so, because of this problem simplicity, and we don't have any other horizontal forces, then we kind of obtain this result kind of right away. All right, so now let's sum up the forces in the y direction. And so in the y direction, we have Jy acting vertically. Okay. We also have Fm, which is acting vertically, minus Wa minus W, and that equals 0 as well. Okay. And so this one we can't solve straight up because we have two unknowns in this equation. So we don't know Jy and we don't know Fm either. Okay. All right, and so the last equation that we're going to do is we're going to sum up the moments in this situation. And so remember, when you're summing up the moments, you have a choice of where you want to sum up the moments around. And so in other words, you have a choice of where you want to include the pivot. Okay. But for these problems, because we're always going to be looking at some kind of body segment interacting with the joint, the best location to sum up the moments around is the joint. Okay. And why is that? And the reason for that is that, remember, two of our unknowns here are Jx and Jy. And so if we sum up the moments around the joint, then Jx and Jy don't even show up in the equations at all because those are acting directly at the joint. Okay. And so actually, oftentimes, it's actually good to start with the moment equation because that'll let you often solve for the muscle force kind of straight up, just like that. All right, and so let's go ahead and sum up the moments around the joint. Okay. And so I'm going to consider counterclockwise moments to be positive, while clockwise moments, I'll consider that to be negative. Okay. All right, and so first we have the moment from Fm. And so the moment from Fm is going to be Fm multiplied by the moment arm, which is Lm. Okay. And since this Fm here wants to rotate the limb counterclockwise, then I'm going to keep this, the sign of this as positive. All right, and so now we have the moments from the weight of the arm and the weight of the object. Okay. And so for the weight of the arm, the moment for that is going to be Wa, La. Okay. Right. Again, it's just the product of the magnitude of the weight of the arm multiplied by its moment arm. And then finally, we also have the moment contribution from the weight of the object. Okay, and then just like before, we're going to take the product of the weight of that object and its moment arm, which is Lw. Right, and so this will give us our third equation. All right. And so, if you look at this last equation that we wrote, you can kind of see why that we chose to sum up the moments around the joint, because the only unknown in this equation is the muscle force, right? Because presumably, you know, everything else we can kind of measure straight off the situation, right? And so most times you can weigh your arm to know how much it weighs. You of course can weigh any kind of external object that you're going to be carrying in your arm. Okay? And then the moment arms most of the time are going to be known quantities as well. Okay? And so the only unknown that we have here is the FM. And so we can just go ahead and solve this equation straight up for FM. Okay. Any questions on this? Okay. Okay. So let's go ahead and solve that last equation for FM. Okay. And so if we add the two weight terms to the other side of the equation and we divide by LM, what we get is FM is equal to WA LA plus W LW all divided by LM. Okay. All right, and so before we go ahead and set and solve for the joint reaction forces, let's go ahead and examine this equation here, and we'll see how the value of FM, how the value of FM changes when each of these other variables change. All right, so let's start with the weights. Okay. And so you can see from this equation here that WA and W are both positive and in the numerator. Okay. And so what that tells us is that the force that the muscle has to exert is directly proportional to the weight of what it's supporting. Okay. Okay. And so if the weight of those objects go up, then the muscle force also has to go up. But then if the weight of the objects go down, then the muscle force has to it doesn't have to exert as much force in order to keep it within equilibrium. Right? And so that makes sense, right? And so the same thing could be said about the moment arms for the loads as well. Okay? And so the longer your moment arms, or the longer your arm is, then the more force that the arm muscle has to exert in order to prevent rotations from happening. Okay. And so if you compare, two people where one person has a shorter arm than the other one, then the person with the shorter arm, their muscles are not going to have to work as hard in order to lift their arm and to do any kind of weights just because their arms are shorter, and the moment arms are shorter. Okay. All right, and so finally, let's look at the denominator. And so in the denominator we have LM. Okay. And so this tells us that FM is inversely proportional to LM. Right, and so what this means is that if LM goes up, right, so if the muscle attaches further away from the joint, then the amount of force that's required actually goes down, right? Okay? And then vice versa too. And so if your muscle attaches closer to your joint, then your muscle is going to have to exert more forces in order to counteract that balance. Okay? All right, and so this last point here actually has some pretty important implications, because for most muscles in your body, that attachment distance, or the distance between the muscle and the joint, is actually really small. Okay? And this is especially true for cases where if you compare it to the moment arms for any kind of external load that the arm is supporting as well. Okay? Right? And so if you look back at the figure for this problem, then the moment arms for both the weight of the arm and the weight of the object are much greater than they are for the muscle moment arm. Okay. And so at first glance, this might seem like a big disadvantage, because the muscle is attached so closely to the joints compared to any external loads. That means that the muscle, and you'll see that when we actually plug in numbers to this, the muscle is going to have to work a lot harder and exert much more force compared to the weight of any kind of external loads, right? And so even for some pretty modest loads, right? And so let's say that the weight of the object that we're supporting is only about 80 newtons, okay? And so with this configuration here, you'll see that the muscle force actually has to exert almost 10 times as much force as any kind of external object. Okay. And so first, this might seem like a disadvantage, right? And so, because your muscles are attaching so close to the joint, they have to produce so much force, even to just support modest loads. And so, it kind of begs the question, why weren't we designed better, right? So why don't our muscles attach, further away from the joint, so they don't have to work as hard, in order to support any external loads? And so I'll answer that question on the next page. But before we do that, are there any questions on this so far? Okay. All right. And so let's talk about that point a little bit more. Okay. Because the fact that they the fact that they attach so close to the joints right now means that the amount of force that they have to exert is very high. Okay, and so I'd say there's kind of two main reasons for this. Okay, and so the first factor is you can call it aesthetic, but there's also practical implications too. And so the first reason is that it kind of reduces the form factor for the human body. Okay. And so what I mean by that is, because your muscles attach so close to the joints, your limbs are still relatively slender, right? And so imagine if your biceps, instead of attaching, right next to your elbow, imagine if it attached close to your wrist, right? And so you have this big just chunk of muscle just in your, that's on your hand. And so you almost it'll almost look like you have like a bird wing because you have that kind of big muscular flap. And so same thing with same thing with your legs as well, right? And so that's one aesthetic way or one aesthetic reason why that we do that. But of course, it has practical implications too. And so if you can imagine if our bodies were just so much more wide, just because of our muscles are attaching further away, then we wouldn't be able to squeeze into a lot of places, and that has evolutionary downsides as well. Okay. But the other reason why muscles attach so close to the joints actually is a pretty mechanical one, right? And so by attaching so close to the joints, what this allows for is it allows you to move. It allows the body to move its body segments really quickly if it has to. Okay. Right. And so, because your muscles attach so close, right, they might have to exert a lot of forces, but then, once they exert those forces, you can actually move your limbs, with the great amount of speed. Okay. And the reason for this has to do with moment of inertia. Yeah, it actually can be pretty significant, and I'll draw you an image to kind of show you why. Okay, and so let's consider two situations, right? And so I'm going to draw a drawbridge. Okay, let's draw two of them. Okay. And so for the first drawbridge, let's say that we are pulling it up here, okay? Right. And so for the other drawbridge, let's say that we're pulling it right here, okay? All right. And so what's the difference between these two situations, right? And so they both are going to want to rotate the drawbridge. And so let's say that we have our joint, or let's say that it's rotating around this limb right here, okay? And so this distance right here is, we'll call it RB for R big, and then we'll call this one RS for R small, okay? All right, and so obviously, from these images, you can see that R big or RB is going to be much bigger than RS, right? And that's kind of the main difference. And so we'll assume that everything else is the same, okay? And so for the first situation here, where you're moving you're rotating the drawbridge with RB, okay? This is going to have a fairly high moment of inertia. Okay, because remember, whenever you're applying a moment or a force, a moment around to rotate something, you have kind of an equivalent Newton's second law for rotation, right? And so that Newton's second law for rotation might be something like, let's see, the torque is equal to the moment of inertia multiplied by the angular acceleration. And so it's almost like F is equal to ma, but it's the rotational version, right? And so for the rotational version, we have torque is equal to moment of inertia times acceleration. Okay? And so for the first situation here, our moment of inertia is actually fairly big because there's several different formulas for moment of inertia, but they all kind of have the same quality where the moment of inertia typically scales with the radius squared. At least, right? Okay. And so the farther away, your action point is, then, the amount of extra torque that you need is actually, going to be increased by a quadratic amount. Okay. Whereas if you compare that for the second example here, okay, where the distance RS is much smaller, this is going to result in a much lower moment of inertia. Okay. Right. And so that lower moment of inertia means that we can actually, increase the angular acceleration of this drawbridge, much faster than the first example. Okay. And so, of course, in the second example, we have to exert a much bigger force just to get it, moving in the first place. But then once you get it moving, then it's you can rotate it with a great amount of speed because, because of that low moment of inertia, then that angular acceleration is going to be much higher in the second case. Okay. And so it's kind of almost like a design trade-off that the human body made, where, we made the attachment angles or the attachment locations really small for your muscles, okay? And so your muscles have to work, pretty hard to actually move them. But once you get them moving, then you can actually move them pretty fast because the apparent moment of inertia that the muscles feel from the limbs is fairly small because that distance is so small. All right, question. So does that mean more torque means more faster movement? Yeah, absolutely. Yeah. And so, the effect is kind of double-fold, for having a close attachment angle. And so even just to get the muscle moving, you have to produce a fairly high amount of torque, right? Because that distance is so small. But then once you produce that high amount of torque, then, you start to rotate, pretty quickly because the moment of inertia is so small. And so the more torque, of course, the more torque that you can produce, then the faster rotation that you can have for your muscles. Yeah. Mm-hmm. Okay. Any questions on this? Okay. All right, and so that's kind of the evolutionary reason why we have our muscles attached so close to our limbs. Okay, and we're not the only ones. And so if you look at a lot of animals in the animal kingdom, they kind of have all the same structure. Where if you look like a cat or a dog, or maybe like a lion, right? They all have fairly compact limbs where the muscles attach close to the joints, just so that they can optimize for fast movements, relatively speaking. Okay. And so that's the muscle force, right? And so we actually aren't done with the example yet. And so the last thing we need to compute is the joint reaction force in the y direction. Okay. And so this is fairly easy because we've already solved for the muscle force. Okay. And so Jy is equal to W, the weight of the object, plus the weight of the arm minus the muscle force. And the muscle force is WA LA plus W LW divided by LL. Okay. All right. Okay, and so now we have a variable expression for both the muscle force and the vertical joint reaction force. Okay, and so let's plug in some typical numbers in here just to kind of illustrate, the relative magnitudes of all these things. Okay. And so all of our input parameters are WA, W. We have, and then we have all the lengths, and so we have LM, LA. LW. All right, so let's assume that the weight of the arm, we'll just put it at a modest 20 newtons. Okay. And then the weight of the object that the arm is supporting will set that to be 80 newtons. Okay. Right. LM will set this equal to 4 centimeters. Okay. And so the bicep muscle is attached at 4 centimeters away from the elbow joint. Okay. And so for LA, we'll plug in 15 centimeters. And then for LW here, we'll plug in 35 centimeters. Okay. All right, and so plugging in these numbers, we end up with the following. And so FM in this case is 775 newtons. Okay. I just plug these numbers into this formula here. And then JY ends up being a force in the negative direction. Okay. And so this ends up being a negative 675 newtons. Okay. All right. All right, questions. How come the length of the arm isn't in the middle, assuming that the total length is 35? And so for the length of the arm, that's just the weight of the forearm. And so we're assuming that the object is being held at the inside the hand. And so there's the length of the hand that gets factored in as well. Yeah. Mm-hmm. All right. And so from this, you can see that, even for a modest weight object, and so, even though the weight of our object here is only 80 newtons, our muscle force has to exert almost 10 times this amount in order to support it. Okay. Right. Another thing I want to look at is the direction of the joint reaction force. Okay. Okay. And so our joint reaction force, we got a negative number here. Okay. And so what that tells us is that the elbow joint is placing a downward force on the arm, okay, on the lower arm. Because remember, the free body diagram that we drew was of the forearm, basically. Okay. Right. And so a fair question to ask is that, is this joint reaction force, does that mean that that this action here is going to be stabilizing or destabilizing? Remember, we talked about stability in joints, right? And so, a stabilizing force would mean that the net contribution from the muscle force and all of the external forces, a stabilizing force would mean that that everything is going to be pulling the bones together at the joint. Okay. Whereas a destabilizing force would mean that the bones are being pulled apart. Okay. And so the question now is this, because we got a negative reaction force here, is this stabilizing or destabilizing? Think a bit carefully for this one, because it can be a little bit tricky, right? And so, take a look at how I worded this sentence here, right? And so, the elbow joint is placing a downward force on the arm. And so the elbow joint is trying to push the arm away, in order to maintain equilibrium, right? And so if we can draw, go ahead and draw right here. Okay. And so we draw the lower arm like this, okay? Then, the joint is basically pushing it down just like that, okay? And so in order for the joint to be pushing it down like that, then the net force has to be pulling the arm into, up there, okay? Whereas the upper arm bone is right here, okay? Okay. And so because this reaction force is negative, okay, that means the net effect from all the other forces is going to be upwards, right? And in particular, it's because the muscle force here is so high that it actually pulls the bone upwards like that, okay? And so because of that, because we have a negative joint reaction force here, that means that this, the net effect of this is that it's going to be stabilizing, okay? Because the arm muscle force is pulling the lower arm up into the elbow joint, right? That's going to stabilize the joint even more because you're pushing the bones together, okay? Right. It might seem a little counterintuitive because we're holding vertical weights in our arm, so you would think that because those external forces are pushing downwards, then that's also going to try to pull pull the bones away from the joint. But because the muscle has to exert so much force, that the net effect of that is that it's going to be stabilizing. All right, question. So because FM is greater than JY, it's stabilized. It's not that FM is greater than JY. It has to do with the direction of JY. Right? And so because this is negative right here, that means that the elbow joint is placing a downward force on the joint. Yeah. And so when you're doing these problems and you're determining whether the joint is being more stable or less stable, look at the directions of the reaction forces and see whether that the net effect from everything else is pushing the joints together or pushing the bones together into the joint, or if they're pulling them away. All right, any questions on this? Okay. All right, and so that's our first example here of static biomechanical analysis. Okay, and so let's do a few more examples, just so that we can get used to this. Okay. All right, and so in particular, let's step up the complexity for this next example. And so for the last example, we had only one singular muscle force that was acting. Now let's consider a little bit more realistic situation where we have multiple forces acting at the joint. Okay. All right, so let's look at the same elbow joint again, but instead let's consider two more muscles. Okay. So let's say that we have our elbow in 90-degree flexion, just like before. Okay, so here's our joint. Here is our lower arm, and there is your cartoon fist. Okay. Okay, and let's say that we're just like before, we're supporting a weight W. Okay. All right. And so in the last example, we only looked at the effect of one muscle. Okay. And so that muscle was the biceps brachii. But in reality, you have other elbow flexors that can help you with this, that can aid with this motion. Okay. And so two other muscles that we can look at are one is called the brachialis. And then we'll look at a third muscle called the brachioradialis. Okay. All right, and so we're going to solve this problem for the exact same things. And so, what we're interested in this problem is all the muscle forces. Okay. And so in this case, we have 3 of them. And so we'll call them, I'll call them FM1, FM2, and FM3. Okay. And then just like last time, we're also going to compute the reaction forces at the joint. Okay. All right. And so just like last time, I'm going to start with a clean free body diagram. And so let me go ahead and draw the arm as a stick. Okay. Okay. And just like before, let me go ahead and draw in our joint reaction forces. And so we have JX, JY. Okay. We have the weight of of the object. We'll call that W. And then just like last time, we have the weight of the arm, just like that. All right. So now let's go ahead and start drawing in the all the muscle forces. Okay. And so we're going to assume the same configuration for the biceps brachii. Okay. And so we'll call this FM1, acting like this. Okay. Next, let's do FM2. And so FM2, we're going to assume is not acting vertically. And so we're going to assume that there's an angle to this. Okay. So let's say that FM2 looks like that. Okay. For this angle right here, we'll call this theta 2. And theta 2 here is the attachment angle for the brachialis muscle. Okay. And then finally, we have our brachioradialis. And so let's say that it acts over here. And then we'll say that it acts with an attachment angle theta 3. Okay. All right. And so I kind of ran out of space here, but we're going to assume that we know all of the distances between each of these forces and the joint as well. Okay. And so let's say that, the distance between here and FM1, we'll call that L1, okay? The distance between the joint and FM2, we'll call that L2, okay? And so, we'll follow that kind of naming convention for everything. And so I don't want to clutter this image too much. And so, I won't list any more than that, but, you can assume that we know all those distances. And so the only unknowns, or all the unknowns that we're solving for, are FM1, FM2, FM3, JX, and JY. Okay. Right. And so just like we did with the last example, we're going to write out the equilibrium equations for for this for this situation. Okay. And so that's going to be some of the forces in the X direction, the Y direction, and the sum of the moments around the joint. All right, any questions on this? Okay. All right, so let's go ahead and do that. So let's go ahead and sum up the forces in the x direction first. Okay. So this one's a little bit more interesting because we actually have some horizontal components. Okay. And so we have Jx, which is the reaction force at the joint. Then we have Fm2 times cosine theta 2, okay, minus Fm3 cosine theta 3. Okay. This is all equal to 0. So that's one equation right there. Okay. Then we have the sum of the forces in the y direction, and so that's going to give us Jy plus Fm1 plus Fm2 sine theta 2 plus Fm3 sine theta 3. Okay. And then we have the weight of the arm, so minus WA minus W, which is the weight of the object, and all that's equal to 0. Okay. All right. And then finally, let's sum up all the moments around the joint. Okay. And so for this, same convention as last time. Counterclockwise moments are going to be positive, and clockwise moments are going to be negative. Okay. Okay, so we have Fm1 L1 plus Fm2 L2. But for this one, we add a sign modifier because the muscle doesn't, or the muscle force is not perfectly vertically up. Okay, and so that's going to be a modifier of sine theta 2. Okay, right, so same thing for Fm3. Okay, so we have Fm3 L3 sine theta 3. Okay. Then we have the moments from the loads. We have minus WA LA minus W LW. Okay, and this is all equal to 0. All right. And so those are all our equilibrium equations. Okay. But and you might have noticed this from the beginning of the problem that we have an issue here because we have three equations here, right? 1, 2, 3. But we have 5 unknowns, right? And so we have Jx, Jy, which are unknowns, and then we have all 3 of the muscle forces, right? Okay. And so we don't have enough equations to actually solve for all of our unknowns in this case. Okay. And so what we have is a very, a very textbook case of a statically indeterminate system. And so in order to actually move forward and to actually start computing a solution, we need to make some assumptions and get some more equations. Okay. Okay. And so I'll give you kind of one of the more common assumptions that we can make. It's a pretty, if you think about it, it's a pretty intuitive assumption. But after that, I'll also go over one other method that we can use to solve these kinds of systems called optimization. But the thing with optimization is that you kind of need a computer to do it. So you would need kind of like MATLAB or some other kind of programming language like Python in order to solve that. And so, MATLAB was not a prerequisite for this class, and so I'm not going to make you do this. But if you're interested, then I'll talk about it just in general about what it seeks to obtain. And if enough people are interested, I can write up maybe some test code to kind of show it in action as well. Okay. But we'll talk about the assumptions that we can make first, and then we'll talk about optimization. Okay. All right. So, are there any questions before we move on? Okay. All right. So let's talk about some of the assumptions that we can make that'll give us more equations to solve for this. Okay. And so, one of the key assumptions, and this one's fairly intuitive that we can make, is that the amount of tension or the amount of force that a muscle can output is directly proportional to its cross-sectional area. Right. And so if you recall from the muscle biomechanics section that, the larger a muscle is, the more sarcomeres, so the more, protein filaments it has. Okay? And so the bigger the muscle is, the more force it can develop. And so, we can see that kind of visually, looking down at a few people down the street, right? A bigger person will punch you harder than a smaller person, typically. Right? Okay. And so mathematically, the way that we can formulate this is to say that the FMs, or FM1, FM2, those are directly proportional to the areas. And so, let's say that we make a comparison between FM1 and FM2, right? And so what we can say is that the ratio between FM1 and FM2, this is the exact same thing as the ratio of their cross-sectional areas. With A1 cross-sectional area muscle 1 was the biceps brachii. Okay. Whereas A2, this is the cross-sectional area of the second muscle, which I think was the brachialis. And so by stating this this relationship with area, this gives us another equation that we can use to solve the problem. Okay, and then you can make a similar ratio for getting FM3 into this. Okay. Okay. And so by saying that the amount of force that muscle 3 can output, it's also directly proportional to its area. Okay. Then we can make another equation that says FM1 over FM3 is equal to A1 over A3, where here A3 is the cross-sectional area of the brachioradialis. Okay. And the cross-sectional areas you can assume are relatively known. And so, you probably won't get a super exact answer because, your muscles are underneath your skin, but you can get a rough idea just by kind of looking and kind of measuring around with the measuring tape. Okay. And so you can assume that you get a roughly accurate measurement for these quantities. And so this is great because these assumptions here gives us the two more equations that we need to solve this system. Okay. And so that's a good thing. Okay. And so now with that, we have all the equations that we can use or that we need to solve for all the muscle forces. All right, and so just because we're running a little bit short on time, I'm not going to do that. But you can imagine that we have a system of 5 equations, and given that we plug in numbers for all of our known quantities, then we can use them to solve for all the unknowns in that system. Okay. All right. Any questions on this? Okay. All right, and so that's an assumption that you can use. Okay, and so if you wanted to solve the equations exactly, then you can use this assumption to get 2 more equations. Okay, but another way that you can solve these statically indeterminate systems is through optimization. Have you guys heard of optimization before? Like when you're talking about statically indeterminate systems in like your statics class or your strength and materials class? Okay, so you guys are kind of familiar with it. And so the idea with optimization is that this is basically a computational technique that will basically solve for the best set of variable values to solve your statically indeterminate system. Okay. Okay. And so oftentimes you're going to use optimization in cases like this, where you have more unknowns and not enough equations, or it can be used in the opposite sense too. And so there's actually cases where you can have too many equations and not enough unknowns for that too, right? And so that's you can use optimization in those situations too. So basically, whenever you have a mismatch, you can use optimization. Okay. And the idea behind it. At least from a biological perspective, the rationale behind this is that whenever you have multiple muscles working on the same limb, and they're all producing the same action, you can consider that as kind of like a redundant system. Right? Which is good. Usually if you're, if you have a big, complex engineering system, you want to build in some redundancy. So, just in case if one thing goes wrong, you have other things to make up for it, right? And so, when you have multiple muscles like this firing at the same time to produce the same motion, okay, generally what your body is going to want to do is that it wants to optimize the amount of work each muscle does, such that each muscle does the least amount of work possible. Okay. And so in situations like this, where you have kind of redundant muscles acting on the same, supporting the same system, your body will just kind of naturally distribute that weight among the different muscles such that each muscle, it kind of minimizes the overall work that's being done. Okay. Okay. Yeah, it smartly distributes the load between the different muscles. Yeah. Okay. Right, and so this kind of problem where you want to minimize all the variables as possible, this is a tailor-made problem for optimization, because optimization is basically an algorithm that aims to minimize a set of variables, subject to a set of constraints, basically, right? And so if you set up this problem within like MATLAB, then MATLAB will find kind of the minimum solution for you. Okay. All right. Any final questions on any of this before we wrap it up for the week? Okay. All right. So I did want to end a couple minutes early today, just to give me a bit of time to distribute the exams. Okay. And so if you're here in the classroom, I have the exams here on this table, so you can come up and get it. Okay. And so besides that, that's all we have time for today. So thank you everyone for coming. Thank you everyone for tuning in. I hope you enjoyed the rest of your weekend. I am working on your next homework assignment, and so it's going to have the stuff we covered with joint biomechanics, but also this stuff too, with the static biomechanical analysis. And so I'm hoping to finish that before the end of the week, and so you can look forward to that probably on Friday. Okay. So have a great weekend, everyone, and I'll see you on Monday.
Thank you, Professor.
I do not. I have an Android phone.
Here, my phone is gonna die soon. Waiting for ready for your long class. Yeah, I mean, I live across the street, so I'm fine. All right.
Yep. See you guys. Have a good weekend.